Hi there. This is a video presentation for my cybersecurity software project. My project is to implement a secure chat application using end-to-end symmetric encryption to encrypt chat content over an insecure medium. User authentication is required to access the chat application. The app should also be able to detect man-in-the-middle attacks such as message modification or replay attacks. Okay, so in terms of the app compiling, I have a folder over here which contains no folders in it, and when I compile this app it will generate a folder with the executable in it. Okay, that shows that it builds correctly. We'll go down here and there it is. Now what I'm going to do is, before I run it, I'm going to make a copy of it, and the reason I'm going to do that is because I have a remote desktop connection over here to a separate computer, and when OneDrive does its thing, the two folders will appear there, and one of those folders will contain an exe I use on my main computer, and another one will contain the exe that I use on the remote desktop connection, MoHP. Okay, so put that away for now. Okay, so we need to register. So the current Windows user needs to have a profile created for them, and in order to access the secure chat app. So if they just go and try and register, there is username checking, and there's also password pattern checking to make sure that there's an increased level of security for the username and password. So if I use user A and then just try any old password, it will tell me that there's an invalid password format and what characters I need to use. So I will use a correct password format. One with the correct length, and then we've successfully created a user pass profile. Okay, now with that profile, now we can log in. So we log in, well, if we don't log in with the correct username or password, it says login failed, so it doesn't give the details of whether it was the username or the password. That's another bit of added security. AA1 ... Okay, so with the correct username and password, we're now in the app. Now, in terms of inviting another person to the app, I expect the details to be sent via an SMS or secure email to the other person, so we can invite another person to the chat. When we press the invite button, we get the details of our network address and our username. Now, obviously, this is not going to work over the internet. This is on a local area network, and we'll copy that to the clipboard, and then we'll come over to the remote desktop. Okay, so we'll run a secure chat on the remote computer. We'll register BBB. Okay, we'll register. Excellent, and then we'll log in. Once again, has to be correct details or it will not work. Okay, so now we're in the chat. Now, we'll assume that the invite has been received, either by SMS or secure or whatever, and we'll paste the invite. So now we have the invite in our address book. Okay, so we have, this is on my local machine, and this is on my remote machine. So let's connect. Username and address 100 102. Connect. So what we've done here is we sent out public key. They received the public key in plain text, and I'll show you that in Wireshark, and then they sent the session key. We've received the symmetric key, which is the session key, and now we're able to chat securely. Now, what I'll show you is in Wireshark, and I'll just make this a little bit bigger. So we're capturing the packets where we're talking on port 1973, which is the port that these apps talk on. So what we've got here is we've got the initial connection, okay, with a little bit of talking. Now, what we've got is the public key, the RSA key value, being sent in plain text, because it doesn't matter, to the other user. The other user then uses that to encrypt the response to send the session key back to the other user. We'll call that person MoHP. Okay. So now we can talk securely. Okay, so if we go hi there gets sent to the other person, and we go hi there back, and there it is. And then you can see that the conversation is encrypted. Okay, it's encrypted. So that's achieved the requirement of symmetric encryption of messages between the parties. Okay. Excellent. So, what's next? For key exchange security, a new public key is created each time the apps run. For symmetric key security, a new key is created each time the apps run. These keys are not stored. Okay, so we've shown plain text handling of public key, showing encrypted sending of messages. Okay, so what we'll do is show you the example of a man-in-the-middle attack. Okay, so we will run, let's close this one. Yeah. And we'll close this one too, and we'll create a new connection. Okay, so I'm going to run it from inside VS Code, because I want to be able to show you how the code works. Okay, so username AAA and AA dot. Okay, we're in. We'll run this one again. BBBB DB1 dot. Okay, and you're in again. Now, what I want to do is I'll show you the code where tampering of a message takes place. Okay. So, yep, excellent. So where are we? Tamper. Okay, so when we send a tampering attack, what we're basically doing is saying this is the original message, and then we prepare the message. Okay, now when we prepare the message, what we're doing is we're taking a hash of the message, and we're also adding in the like message count. Okay, and then we add them together to the actual message itself, and then we encrypt the message and send it. Okay, so that's what prepare message does. So what we're doing with the tamper attack is we're going prepare the message, and then we go tamper equals false by default, but now we're saying actually tamper with it. So what we're doing is we've calculated the hash, we've converted the message count to the string, but we've changed the message. Okay, and so the message no longer matches the hash, and then we've put together the message, and then we've sent it. So that's what we're going to do from MoHP, and then we're going to show you that it detects it. Okay, so we'll go back to Next one, we connect. Okay. And we've got our app over here. Right, so we're connected, we've got the session key, we're chatting, la-di-da, and la-di-da, and then our man in the middle has changed the message. So this is the original message, and this is the original message that's been modified, and it has discovered that it's been modified because the hashes didn't match. So if we look up validate message, there we go to the definition, we calculate the hash, we go, is the hash that we got from the unencrypted message the same as the hash of the current message? If not, message has probably been modified. Okay, now let's try a different kind of attack. I'll show you the source code for this one first. It is replay attack. Okay. So what we do is each time we get a message, each time we send a message, we save it. We save the encrypted version of it as the last message sent. And this is the same way that a replay attack would be run. So if we say, if the replay attack button is pressed, then we go send replay attack, and we go send client message. We're playing the last message packet, and it's the last sent message packet. So that is basically exactly the same. It's the encrypted version of the message ID, the hash, and the message. So that's what we'll do here. We'll go send a message. Hi there, we've received the message, and then we go launch a replay attack. So we're playing the last message packet, and look at that, we've got the same message again, but it said the message is probably a replay attack. Now the reason it does that is because we have a look at validate message again. Validate message checks if the message count is less than or equal to their message number. Okay, because each message number should increase. So we set it at a random number, but each message that gets sent increases the message count which gets added to the message before it gets encrypted. So what we've done is when we play a replay attack, the message count of the received message is equal to the last message that got sent, right? And so because of that, if any previous message gets sent, then it gets identified as a probable replay attack. Okay. So finally, when we close the app, okay, the settings files are saved. I'm going to close this one too. The settings files are saved in the local folder. Okay, now that contains the profile information, the saved address information, and the log. If you open it, it's encrypted. Okay, so you can't read the details of the username and password, you can't read the details of the addresses, you can't read the details of the logger. The way that it's done though, unfortunately, is a little bit weak. The key for saving these are stored in the app at the moment, where they probably should be in a secure store, a Windows secure store or something like that. Okay, and that's the demonstration. Thank you.